Good morning, good afternoon, and good evening, everyone. Welcome to today's Ask the Expert webinar on materials characterization and failure analysis using Plasma FIB. Our presenters and experts for today are Dr. Mike Salmon, our scientific fellow, Sarah Wang, dual beam team leader, and our moderator for today, Yan Zhu, dual beam manager. We're also very excited to have Dr. Adam Stokes from Thermo Fisher joining us in our live expert panel at the end of the presentation. My name is Rena Samsu, and I am the Senior Marketing Manager assisting with today's event. Before we get started, let's go over a few housekeeping items. All attendees have been muted. However, if you have any additional questions that pop up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation. Time permitting, we will answer these questions during today's event, or we will follow up with you in the coming week. With the abundance of pre-submitted questions for today's event, we unfortunately will not be able to get to all of them during the presentation. For any unanswered questions, the team will send answers out to those questions soon. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to our first presenter for today, Mike Salmon. Mike?
Thanks, Rena, and welcome everyone to the webinar today. So for today's agenda, I'm gonna give a very brief company background, and then we're gonna get right into your Plasma FIB questions answered. We'll have a little additional Q&A at the end where Adam comes back on and can help answer some of the questions, and just a brief summary of the overall talk. So Eurofins is a global leader in testing with more than 58,000 employees in 900 laboratories over 54 countries. And Eurofins EAG is then a division of Eurofins that specializes in materials testing with over 40 years experience. We have more than 600 employees in 20 laboratory facilities all over the world, and we have more than 2,500 different types of testing equipment and support over 4,000 clients. So let's see here. So you may have seen this chart before, but let's take another look at it for those of you that maybe haven't. This is called the EAG SMART chart. SMART is an acronym for spectroscopy, microscopy, analytical resolution tool. And this chart summarizes the majority of the techniques we have available at EAG. And this allows you to quickly compare the spot size and detection limit of each of the techniques. And they are also color-coded according to the descriptions at the lower left. For example, dark blue techniques primarily involve or primarily provide elemental information, while green ones provide imaging information. The x-axis shows the range of spot size from 1 centimeter down to 1 angstrom, and then the y-axis shows concentrations either in atoms per cubic centimeters at the left on this side, or in parts 10. In concentrations that range from 100% at the top down to 10 parts per trillion at the bottom. So within this box, you can select your technique based on the detection limit required and the size of your area of interest. So outside of the box, you'll notice there are techniques that don't quite belong in the chart. The techniques to the right, for example, don't necessarily have a spot size associated with them. They're considered bulk composition techniques that may actually consume your entire sample, and thus they have only a detection range shown from top to bottom. And then the techniques at the bottom are imaging techniques and don't provide compositions per se, but they do have relevance with respect to the spot size on the x-axis. And today, this is where we find the techniques we're talking about today, FIB and PFIB. If we take a zoom in here, we can see that FIB and PFIB cover a range from now about, I don't know, down into the 5 nanometer up to now 1 millimeter range, with PFIB really extending that ability to go from somewhere in the 50 micron range now out to 1 millimeter. And this is going to be the basis of what we're talking about today. And even though it's listed here as an imaging technique, we're going to show and you're going to see how much more it really is than just imaging itself. And so one of the big, questions it was asked by many people were just to give some basic background on FIB. So what is FIB exactly? And FIB stands for focused ion beam. And so this is the industry standard for making localized material analysis, especially for semiconductors, for things like SEM cross-section prep, STEM or TEM prep, doing 3D visualization and volumetric analysis. And one thing I'd like to point you guys to is this great book on focused ion beams for a lot of background info by Giannuzzi and Stevie. And the one thing important to note here is typically gallium is used as the ion source for these types of instruments. And then a typical FIB has three main functions. We have milling or sputtering, where we're going to use this focused probe of high energy ions to remove material from our sample. And that looks a little something like this, where we can progressively come in and then remove that material to see a cross section. We can also use this ion beam in addition to some gases that are injected into the system to actually deposit films, whether they're metals or insulator films. And so we typically use this all the time for almost every analysis to deposit protective capping layers on the surface of the sample. And then not only that, we can actually use it for imaging as well. And there's some unique aspects to the imaging. It's much more surface sensitive than with electrons. And then you can get also some very enhanced channeling information in polycrystalline materials, such as this image here. And so it's important to really realize that we always have to create sort of optimized beam conditions for each of these functions as well as per sample basis. And it's, even though it's highly localized, it is a destructive technique. And then this is really why this led to the creation of dual beam instruments, where they merged an SEM, a scanning electron microscope, with the focused ion beam. So you could do all the work with the focused ion beam and then non-destructively view that changes in the sample. And then, so that leads us to then, what is PFIB? And so PFIB is a special variant of focused ion beam that stands for plasma focused ion beam. So we're gonna, instead of using gallium, we're gonna use an inductively coupled plasma source. And there's a variety of different gases that are available. And this was commercially available starting in around 2012. So we've had about 10 plus years of development commercially of this technology. And it's now much more refined and integrated with state-of-the-art SEMs in a dual beam configuration, as I'd mentioned. And you can find more information about PFIB from our previous webinar at the link below, or this QR code here. And while there is a variety of gases available in the Hydra product from Thermo Fisher, we're going to specifically primarily focus on use of xenon today in this presentation. So Sarah?
Great. Thank you so much for the intro, Mike. We're going to be jumping into some of the questions that were submitted over the past few weeks about the PFIB. So we've kind of split them up into different themes, and one of the most commonly asked questions were, can you compare PFIB versus conventional gallium FIB, and what are some of the differences in the resolution for imaging? So here's a general comparison between a conventional gallium liquid metal ion source, which is a point source, and a xenon inductively coupled plasma broadbeam source. So one of the main differences that we've highlighted below is the maximum achievable FIB current. So for gallium, for modern columns, typically we can get up to 65 nanoamps of current out of a gallium FIB. But for plasma FIBs, we can get up to 2.5 microamps of current, and this number is also expected to go up for newer FIBs. So essentially, it's a 40 times higher maximum beam current for plasma FIBs, and this allows us to remove much more material more quickly than a conventional gallium FIB. Another question we received was regarding the imaging resolution differences between the two beams. So for gallium FIB, the probe focusing technology is really mature, and we can get to image resolutions of under 4 nanometers, which allows for very sharp imaging and also very sharp milling for site-specific sample prep or fine cross-sectioning. For plasma FIBs, we do have a larger probe size, and the image resolution is around 15 nanometers at best. But this doesn't necessarily correspond to the milling resolution, which also depends a lot on the beam profile itself. And for plasma FIBs, we do see that the beams have larger beam tails, so more protective methods such as capping layers and other techniques are needed to maintain a nice cross-section for the plasma FIB probe. So another question we got was, how do material removal rates compare between plasma FIB and traditional liquid metal ion source FIB? So as I mentioned in the last slide, PFIBs can produce 40 times higher maximum beam current than gallium FIB. So this is an example of using the maximum beam current for the two types of FIB to see the maximum removal volume of the same material system. And you can see with PFIB, we get about 2 orders of magnitude higher than gallium using the maximum current. There are also some differences in the actual sputter yield per ion species, but the largest contributor to the bigger volume that we can remove is that higher achievable beam current.
So the next question that folks asked, quite a few of, is are there further new applications of PFIB thanks to this scale or improved removal rates that were previously not achievable with gallium FIB? And so the answer to that is of course. So we can really scale up the amount of material we can interrogate for analysis, specifically cross-sectioning, for instance. This is an example of where we can make much larger cross sections at very specific sites in a sample. So really typically previously making cross sections or many cross sections that are much bigger than 50 microns wide by maybe at most 30 microns tall would be really far too time consuming for gallium FIB. And we'd have to rely on mechanical cross sectioning first or some way to get close to the areas of interest. And in many cases, that still is one of the more straightforward routes to go. But as advanced packaging continues to evolve and we see more and more dissimilar materials coming together with non-flexible components made into flexible ones, metals and insulators, etc., this can cause a lot of issues for mechanical cross-sectioning, and it can introduce a lot of artifacts to the analysis. So this is just an example of showing how we might use PFIB to do this kind of target analysis. This is a specific silicon processor. So we've delitted the processor initially using mild heat to remove the indium thermal connection. And then we've used micro CNC machining to planarize the back substrate and get it thinner so we can get it a bit closer. So originally this is about 1 millimeter thick. And so we're going to try to get that down to like 100 microns or so. And then from there, we can use techniques like X-ray imaging, or in this case, infrared imaging, to then map out where on the chip each of these types of devices might be. And in this case, we were interested in the chip substrate connection in the lower left corner here, where we noticed that there was some delamination occurring, as well as to then see, what kind of quality we could get in the cross-sectioning using very large beams. And so here, this is the corner where we're seeing some delamination between the potting material and the chip itself. And so this is where we've planarized it with a CNC machine first. And then this is an example of the cross-section we made here, approximately 500 microns wide by, 150 microns deep or so. And so we were getting into the first bit of interconnect and the connections between the PCB board below with a copper pillar up to the chip itself. And we can actually see then in the cross section, we have very good continuity between this copper pillar and the device. And then we can look a little bit closer at higher resolution at the device level and the overall interconnect on the chip, so we can see the many layers of metal as well as where they connect into the devices itself. We have very good resolution here and cross-section quality, actually. And this is without any sort of extra work. This is just xenon cross-sectioned. And so we get a little bit of advantage that we have this very thick amount of substrate material above the device layer. But you can see that we can't really avoid curtaining altogether just in a regular cross section here in the below layers, as some of these differences in density of the metal layers and the insulators then cause this sort of curtaining effect or striping. And Sarah will talk a little bit more about that in the coming slides, about how we can avoid this and improve on the cross-section quality, especially for deeper structures. So another question that came in was, how can you use this for paint and pre-treatment failure analysis? And we have some examples to look at this as well. This is a case of looking at a commercial paint on aluminum, I think for aerospace use or aeronautics use, not necessarily aerospace, but effectively here we have about a 35 micron thick paint application on aluminum within a pre-treatment at the surface. And so then the question is can we make a very large cross section that can span surface defects that we see like this to see the extent of these defects? We want to look at the uniformity of the paint itself, maybe look at the interfaces, look for porosity and or delam. And here you can see we've made a large, over 200 micron wide cut in the paint down into the aluminum, about 50 microns deep. And then we can utilize the different SEM signals to look at the paint structure itself. We can see that the defect is actually very surface related, so it's not too much of an issue. So there's some sort of residue in the process that ends up surface, but we can then look at the pre-treatment layer below, and then we can see that there's a variety of particulate or pigments within the carrier and the polymer fill. And so then if we switch to backscatter imaging, we can actually see there's sort of two different communities of particles in this particular example. And we can look a little bit more high resolution at that, and we can see that there's actually one type of particle is a very layered structure, and then the other is smaller and round and has a slightly different atomic number. And so lastly, we can look at the interface, so this pre-treatment layer, so we can get very nice high quality images showing we can actually see pre-treatment layer cracking occurring, and you can see that the paint can get down below that. So ultimately this layer isn't completely continuous, there's some breaks in it, and that tends to be important when you're trying to investigate things like delamination, etc. Additionally, we actually could see also some porosity in the layer down below, and it's hard to know whether or not that's actually from the PFIB itself or whether it's inherent in the film. But a little bit later in this talk, we'll talk about how we can also control the temperature of the samples so we can kind of mitigate any kind of thermal related issues.
Great. So as Mike mentioned, curtaining is an artifact that can occur in both conventional and plasma FIB, although the effect for xenon plasma FIB of curtaining is a bit more noticeable because of those larger beam tails. So we got a question that said, what are the best practices to avoid severe curtaining effects at the bottom sidewalls of through silicon vias with depths of 300 to 400 microns? So one technique that is included within our Thermo Fisher PFIB is a rocking angle mill. So with a conventional FIB cross-section, in this default mill picture, our beam is coming straight down from the top, perpendicular to the sample surface. And you can see there are some vertical striations that appear. Curtaining can occur for many reasons. One of the most common ones is having different material hardnesses. So a harder material in a soft matrix or vice versa. And other things, even like grain orientation, can also cause curtaining and this type of streaking to happen, which can make it difficult to see sharp interfaces in your cross-section. So one way to mitigate this curtaining is with a rocking angle mill. So your sample is loaded on a pre-tilted holder, and it's rocked back and forth relative to the ion beam, so that instead of coming straight down, it'll come in from a small angle from the left and the right, and it'll alternate back and forth to create a smooth cross-section. So in this final image, you can see that the cross-section finish is a lot smoother than that of the default mill. and the curtaining is greatly reduced. The question asked specifically for 300 to 400 micron deep TSVs. So with that depth, it will be more challenging to fully remove the curtaining from the bottom of the structure. But by opening a wider trench to fully reveal the structure and also spending a longer time on this rocking mill process, you can still mitigate the effect of curtaining near the bottom of deep features too. Another set of questions we received is in regard to how Plasma FIB can be used in failure analysis applications. So both PFIB and gallium FIB are really versatile tools in the failure analysis space. One of the most common workflows is in FA technique, such as X-ray or hotspot analysis will be used to find a local area that you want to expose with FIB. Because maybe the sample is too delicate to be mechanically cross-sectioned, or maybe the defect is too small to be able to reliably hit with mechanical cross-sectioning or lapping. But now with package devices and a lot of modern structures, the required cross-section depth is becoming deeper and wider. So it is challenging to cut hundreds of microns deep with conventional FIB. It could take several days of continuous milling. But with PFIB and those high achievable currents, we can now perform cuts that are hundreds of microns deep and hundreds of microns wide within just a few hours. So here's an example of a PFIB cross-section on a 3D chiplet looking at the through-silicon vias. So the PFIB is used to create a nice smooth cross-section that's about 300 microns deep. And then the SEM can be used to perform high-resolution imaging on that cross-section face. And through the SEM, we're able to see defects such as voids within the different metal layers that could affect the conductivity of this device. With the Plasma FIB, we can also perform a 3D reconstruction, which we'll go into further detail later. But essentially, the FIB is used to remove a small amount of material, and then a high-resolution SEM image is taken, and then the FIB is used to remove another slice of material, and another image is taken. So this process is repeated a few hundred times depending on your required step size and resolution, and then based on the contrast of those SEM images, you can perform a 3D reconstruction. And this will let you look at things in 3D space, such as, for example, how a crack propagates throughout a sample, or how a pore moves in 3D space, which might be challenging to imagine from just one 2D image. So yeah, PFIB is really versatile for many different types of failure analysis.
So then that leads into the next question, which was, does Plasma FIB mitigate any of the amorphization or ion implantation / contamination during sputtering that's inherent with gallium FIBs? And so this is a little challenging to answer because it's sort of a yes and no. So there's a few things, a few significant benefits to using xenon, for instance, over gallium. The first being, as we mentioned, you have very high removal rates and things like that. But ultimately, with xenon, you're using a much higher Z ion, and this actually provides then for lower penetration in certain materials, especially like silicon. And so that essentially means that more of the damage and the sputtering is confined to the surface area. So the amorphized layer will be much shallower. It's approximately 30% less. And so by then using xenon over gallium, that actually enables a variety of things, especially the delayering in the delayering space and some others where you need lower damage at the surface. It's sort of a critical aspect. And then the other side of it too is that then using xenon, it's a non-metallic, so there's no gallium poisoning. So the redeposition materials that previously contained gallium and the amorphized implanted layer at the surface of the sample is no longer containing gallium, a conductive species. So this really opens up, some new post FIB techniques like the ICD processing, which I'll talk about in a minute, nanoprobing as well, and then things like EDS and EELs, so high resolution analytical work. We no longer have gallium sort of potentially contaminating the results of that as well. And so the first thing I mentioned was how now using this decreased amount of damage layer really then aids in the ability of doing delayering, so we can keep that damage to a minimum as we go down through the sample. And so PFIB plus some proprietary chemistry allows for automated and precise endpointing of this delayering. And so typically what we'll do is we'll do bulk removal of layers that aren't very important to us, so layers that are much greater than 400 nanometers through mechanical means, broad ion beam polishing, which you may know of. But we can also use PFIB for this too, which I'll sort of go into and share. And then, but really the important part ends up being down here when layer thicknesses get less than 400 nanometers. So we can use the PFIB plus DX chemistry to really show that. So for the bulk layer removals, we can use a technique called spin mill. And so in this case, the automated software actually rotates the sample during milling to then remove large planar areas of material, so we can get down to the specific layers that we're very interested in, the deeper layers. And so this gives very good uniformity over, in this case, 100 micron diameter or so. And then from there, we can use PFIB plus DX delayering to go down through this region in the center here, and we can use this stage current as an endpoint detection, so we can stop abruptly right at the beginning of the next layer. And then we can use the SEM and the dual beam to image with high resolution the structure that we're interested in. And so once we're getting down to these layers of interest, we can actually then also combine it back with nanoprobing, for instance, to be able to do different electrical tests. And so since we're using xenon instead of gallium, we're no longer creating additional conductive paths by the implant of the gallium. So we have very good isolation and keeping the inherent structure intact. And so we have different nanoprobing capabilities at EAG, but we have a specific instrument that can provide 2.4 point resistant measurements, and then a variety of electrical tests from EBIC, EBAC, RCI, and eBirch. And I'll talk briefly and show an example of EBAC. So in this case, we're looking for an open in the circuitry. And so we can use PFIB to delayer down to metal 5. We can then carefully probe with the probes in situ in the SEM itself. And so we're then going to use an E-beam to inject current into the conductive paths that we're interested in studying. And then we're going to make physical contact to that path in a specific location and allow then the current to flow to ground through a picoammeter. So then we can use the picoammeter signal as the imaging signal, and we can then see here as we inject the current, we can see that it ends up stopping at this one location here to the right. So we're not making full connection across this. And so this is in this case a metal 5. And so we observe this with EBIC because we can inject down through several layers actually at a time. And then we can use PFIB with DX chemistry to delayer a bit further. So then we can actually then inspect metal 4. And here is where you can see the metal break observed in metal 4. So being able to combine PFIB plus then the electrical test really allows you to isolate and locate very small defects in the sample that previously would be very challenging to do.
So another type of question we received is regarding TM sample prep. So what is your experience preparing TM samples with PFIB? And how well does xenon work for lift outs? Is it a total replacement for gallium? Where is xenon better than gallium and vice versa? So in terms of TM lamella preparation, gallium is still the industry standard, and it works great for a wide variety of samples, especially due to that really focused probe size. It's great for cutting small features and making thin windows. Xenon works fine for most types of TM lamella prep. Of course, if you have a blanket sample, it'll be a lot more straightforward than a site-specific feature. And overall, xenon is not as efficient for sample prep yet as gallium FIB, and that's because you're not utilizing the high current capability of PFIB. Usually for lamella prep, you're using lower currents and lower accelerating voltages to create a thin, damage-free specimen. But every day there are improvements being made on the prep quality and the prep techniques. So this is definitely a skill that can be learned. The main motivation for why you'd want to use xenon PFIB for TM sample prep is to avoid the introduction of any gallium to your system. So because gallium is a reactive metallic species, it can accumulate at interfaces or grain boundaries. It can form intermetallics with different metals within your sample. And if your sample already inherently has gallium, like a 3,5 material, then you wouldn't want to introduce additional gallium into the system if you want to do very high resolution chemical analysis, such as STEM EDS or STEM EELs. Other techniques such as EBIC and cathodoluminescence are also highly affected by the gallium-rich surface damage from conventional FIB, and it can be mitigated by using PFIB, which usually uses an inert plasma species and also has a smaller implantation and amorphization depth.
So that leads you to how good is the lamella prep quality, and how does that prep quality compare to gallium FIB? And so this is an example of aluminum grown on silicon and prepped on the left. This is a stem cross section prepped on the left by gallium FIB and then on the right by xenon. And we can see the difference in the HADF imaging here. Both have very good quality. We have very good atomic resolution in the sample. But here we see how gallium migrates to the interface of the silicon and aluminum there and causes this very bright little layer. And so ultimately, we wouldn't have necessarily known before, unless you do EDS, that this is certainly gallium. And then in this case, if you look at using xenon, now we've removed that artifact from the interface, and now we have a clear understanding of how the aluminum is actually deposited on the silicon. And so ultimately, the quality of the prep is absolutely fine for doing high resolution STEM work. As Sarah mentioned, many optoelectronic devices, containing 3,5 materials contain gallium, and so it's very nice to be able to do these kinds of preps using non-gallium sources. And it's becoming more and more routine. So we're learning how to control the beams better and better, and how to set up the thinning so that we have the most success possible. And then this is just an example showing same kind of thing, prep on 3,5 materials now. So in this case, it's an InGaN multi-quantum well sample from a high brightness LED. So we can see we get very good lamella quality, low damage, ultra thin specimens that are suitable for AC STEM and then subsequent EDS mapping. And in this case, we don't necessarily see a huge difference in the EDS results from using PFIB in this case, but certainly in situations where we see metal contacts and things like that, it becomes more and more important, like I just previously showed, because you get that gallium diffusion to interfaces, and it obscures sometimes the true structure at those interfaces. So the next question was, since it's easier for PFIB to make these larger cuts, would it also allow for larger TEM areas too? And In my experience, it's again sort of yes and no. You can make much larger cross sections and lift outs, but ultimately it's very hard to thin those very large areas uniformly and or without them having significant warping. You have to do a lot of extra things to try to mitigate those kinds of issues. It can be good for lifting out large areas to then search and hunt for, let's say, crystal defects, in which case then you can know where they are and then go back and further thin smaller regions. So for iterative analysis, it does work very well. What do you think about that, Sarah? Do you think you've experienced that kind of same behavior?
Yeah, I totally agree. You can only utilize those higher currents when you're doing the bulk cuts. So you can access areas that are very buried below the sample, or maybe speed up like a plain view TM process. But when you're doing those final thinnings, because you're using low KV and low current, it'll take just as long, if not a little longer, than conventional FIB to make a large window.
Yeah. And so then to sort of piggyback on that, for semiconductor samples, do you find PFIB to be accurate enough for final thinning, or is that better with a gallium fib? I think you sort of mentioned that. It's like for very tight tolerance to like small targets, the gallium fib is still probably better. But ultimately, if you need the analytical information, maybe PFIB will be good enough. I mean, certainly we have the high enough quality to make those samples, but sometimes having that end pointing is really tough to do sometimes in the PFIB as compared to gallium. And then lastly, is plasma FIB better at controlling lamella thickness uniformity than traditional FIB? What do you think about that one?
I think plasma FIB can be used to make a more damage-free specimen, but it isn't necessarily better at controlling the thickness uniformity. Those broader beam tails do typically make it a little more challenging to do like a very thin and uniformly thin lamella. But you can get, nice thin areas with very low amorphization or implantation. So I think it depends on whether you're more interested in high resolution imaging or like high resolution chemical analysis. So the next series of questions is about PFIB capabilities for air sensitive samples, such as battery materials, very reactive elements such as lithium and sodium, or other materials that are very susceptible to oxidation. So with our Plasma FIB system, we do have the Thermo Fisher Clean Connect, which can attach to a glove box. So essentially you can, under inert gas, mount your sample and prepare it for dual beam analysis. Then we can load it into the Clean Connect still under inert gas and pump it down to vacuum through the dual beam chamber and load it in. Once it's in the tool, you can do whatever typical analysis you would normally want to do, such as TEM sample prep or FIB cross-sectioning and SEM EDS. And then that sample can be loaded back into the detachable Clean Connect system and into a glove box for transfer to a TEM grid holder or further sample breakdown, whatever is required. So this has proven very useful for battery materials and perovskites or anything else that you wouldn't want any air or moisture exposure to. Another question asks, why would you specifically want plasma FIB for analyzing battery materials? So with a lot of battery systems, we find that the layers and stack thicknesses are much greater than that of semiconductor materials. So with the plasma FIB and those higher currents, you can get larger cross sections faster. So this cross section is showing a battery stack that's hundreds of microns deep, which would take hours in the regular FIB. PFIB also allows for site-specific measurement of the layers. So if there was a certain area of your battery sample that you wanted to cut, or you wanted to avoid any air exposure or moisture exposure that may be caused by mechanical polishing prep, then PFIB would be a good alternative. With SEM EDS, we can get compositional information from the cross-section face, and we can also get morphological information with the high-resolution SEM imaging. And we can use the PFIB to produce 3D reconstructions from the battery sample, which we'll show it in a later slide. So here's an example of a large PFIB cross-section into a battery using xenon. This cross-section is about 1 millimeter in width and 250 microns in depth, which would probably take several days of consecutive milling to achieve with the gallium FIB. We can see that the final finish of the cross-section is very smooth, and it allows for high-resolution SEM analysis. So when we zoom in and take our SEM images, we can clearly see the cathode particles, we can see the grain structure in backscatter mode, and we can also see the average particle diameter and cracks within the particles that would allow for lithium migration. So it's a really powerful technique to let you correlate the morphology of your battery sample to its performance. With Plasma FIB, we can also perform a 3D reconstruction, which I mentioned earlier in the through silicon via example. But similarly, for any type of sample, including battery samples, we can remove a small amount of material with FIB and take an SEM image and do that sequentially to create a stack of images and reconstruct a 3D volume. So from this, you can get particle statistics such as the average diameter, and the porosity and tortuosity, or how connected the pores are. So this is information that you could not extract from a single 2D image, and you'd really need this type of 3D reconstruction to understand. So continuing on the theme of analyzing beam-sensitive materials, there's also questions about temperature damage of polymers or other inorganic materials, which is a real concern. As you're jumping up to those higher currents in PFIB, you're going to get a lot of localized heating and also potentially localized melting of beam temperature materials, beam sensitive materials. So one way that we can mitigate this type of damage is by using a cryo stage. So both our regular and xenon plasma FIB have a cryo stage attachment that can cool small samples to near liquid nitrogen temperatures. So we show an example here of cutting pure lithium metal at room temperature using our gallium FIB. And within that cross-section face, we see a lot of porosity and a lot of heterogeneous microstructure. If you didn't know any better, you might think that your metal is very porous, but when we do the same cut under cryo conditions in the PFIB, we see that actually the cross-section face is very smooth, and those features were a result of beam damage. So this also works for other low temperature materials. One popular low temperature metal that's being used a lot now is indium, especially for ball bumps. So if you cut indium at room temperature and it's surrounded by a lot of insulating and non-thermally conductive material, the localized heating can be quite extreme and cause indium to melt and delaminate at the interfaces. So you might think that you have poor connection there when actually it's an artifact of localized melting. So that's another popular application for when you'd want to use a cryo stage to preserve the morphology of your sample. And lastly, cryo stage also mitigates thermally aided damage mechanisms for semiconductors, oxides, and soft materials. So for a lot of these types of systems, if you might be worried about shrinkage, if you want to make very accurate thickness measurements, or you might be worried about delam or melting of like adhesive materials. So in all of these cases, cryo can help preserve the sample and reduce thermal beam damage. With our cryo stage, we can also perform full TEM sample prep. So this is an example from pure lithium metal, where the sample is cooled to near liquid nitrogen temperatures. we perform the conventional TEM, trenching, and J-cut. And then we can actually lift out the sample without the use of the gas injection system, which doesn't work at cryogenic temperatures, and attach the sample to a regular TEM grid. And it can then be thinned to electron transparency, still at cryo temperatures for TEM analysis. And we can also perform cryo-TEM or STEM and cryo-EDS and EELS.
So the next question was, are there important applications of PFIB for semiconductor lasers, silicon photonics, or LEDs? And so really this is, the answer to this is yes. So we've talked a little bit about, we can do much larger cuts, so we can investigate things on a sort of a greater scale. We have, no gallium poisoning. So these are all things that are important for this kind of subset of devices. And so, ultimately, in a lot of cases, a lot of modern photonics are hybridization kind of packaging and or flip chip now. So they're trying to put the active layers as close to the heatsink as possible. So that leaves, similarly to the silicon processor example, you have a lot of substrate above the actual active area. So we can use PFIB to actually get down to those areas after doing localization techniques like EL, EMI, or whatnot. And so we can then do STEM cross-sectioning or plan views of those active layers. And then also previously mentioned, so the gallium poisoning really enables things like higher resolution STEM EBIC, where we're working with very limited signals. So typically the FIB induces a semiconductive or a conductive surface current path that essentially shunts the EBIC signal away. So we want to make sure that all our EBIC gets through the detected circuit. And so PFIB can really help reduce that and increase our signal noise quite a lot. And so then lastly, are there any disadvantages to using PFIB compared to the standard FIB technique? And so some PFIB challenges are really that, we're dealing with much greater maximum beam currents than gallium. So we really do have to take into account sample thermal conductivity and whether or not cooling is going to be needed. We need to also really prepare the surface of the samples better, especially if they're important to the analysis. And so they need to be tougher and are much thicker to manage the beam tail issues. And so the workflows kind of have to adapt to this issue too. So we have to come up with creative ways to protect our samples and then to create good surface finishes and cross sections, etc. And then, as we mentioned, that PFIB can suffer from a lot of curtaining without this proper planning, and so we've had to develop updated protocols for using this tool relative to the gallium FIB to really create artifact-free samples, and using things like the rocking stage really help as well. So it is certainly possible. So to summarize, PFIB enables the characterization and failure analysis of much larger volumes in reasonable amounts of time than with gallium FIB, having approximately 40 times the beam current capability. Xenon PFIB plus DX chemistry provides very repeatable, high quality delayering capabilities for both sort of construction analysis as well as further electrical test. PFIB provides this gallium-free alternative for SEM and STEM work and EELS and EDS. And then if you add cryo and environmental capabilities like we have, we can provide cross-sectioning for soft and reactive materials. And so this gives us the ability to do large pinpointed cross-sectioning up to 1 millimeter in scale for construction analysis, for interface analysis, and then for 3D FIB SEM tomography over larger areas like for the battery analysis. And so with that, I'm going to stop, and then we'll have a Q&A session now and try to answer some of your questions that have come in over the course of the talk and things maybe we didn't cover already. And so Jan, I'm going to toss it back to you to manage the questions.
Thank you, Mark and Sarah. Thank you for everyone's time as we continue to the Q&A session. Before we start, I'm excited to announce again that Dr. Adam Stokes PFIB expert from Thermo Fisher Scientific, is joining this Q&A to assist with all equipment-related questions. Please feel free to keep typing your questions as we start answering some of the submitted queries. So first, I have a question for Sarah. Can we use PFIB for anodizing structure analysis?
So for anodized materials, a lot of times it is like a very thick layer, like up to hundreds of microns thick. So PFIB is a good tool for being able to cut deep, and also aluminum oxide is a very hard and tough material to mill. So that's another case where those high currents would be beneficial to perform those types of cuts. And especially for aluminum, if you're worried about gallium accumulating at interfaces, which we see it do a lot at aluminum, then using an inert species like xenon would be good for making TM specimens from anodized aluminum. So yeah, it is a helpful tool in that case.
Great, thanks. There's one question about what materials are challenging or not suitable for PFIB. Mike, could you help to answer?
Oh, wow, that's a tough call. I would say, well, anything that's vacuum compatible can go in the PFIB, and we can obviously try it out. Certainly, we've talked about things can be sensitive to temperature and maybe different irradiation situations. I think that some polymers, you're just never going to overcome it because the damage mechanism isn't thermally, it's not a thermal mechanism, but more of an ionization damage mechanism. And that can be harder to overcome, but we can try different accelerating voltages and currents, et cetera, to try to overcome that or mitigate it. Certainly too, there's some other creative things we can use, these different injected chemistries to try to overcome as well. So I think ultimately, almost nothing is off limits at this point, so.
Great, thank you. And we have questions for Adam regarding the hydro system. So does one of the hydro ion species reduce cross-section curtaining often seen in the xenon ion beam cross-sections?
Yeah, hi, thanks for the question. Yes, we've done a deep dive on this problem, and we've analyzed the differences between, gallium and xenon. And now with hydro, we have the additions of argon, oxygen, and nitrogen. And we really are seeing some good benefits with argon. We're seeing it being able to cut dissimilar materials evenly. And the throughput is right there. So yeah, if you're having trouble milling through dissimilar materials and getting curtaining artifacts, first step would be using argon.
Okay, thank you. And there's one more question regarding the hydro. Does the PFIB support using gas mixtures like oxygen and argon during milling?
Yeah, so the primary ion species is a uniform ion species, so it's just xenon, argon, oxygen, or nitrogen, one at a time. But we can introduce different precursors during that process, like DX that Mike has been mentioning, and other proprietary chemistries as well to go in tandem with it. The primary ion species that we use normally with precursor gas is going to be xenon.
Okay, great, thank you, Adam. So by the way, our webinar mainly talk about the xenon PFIB, but we also have access to the hydro PFIB at our North Carolina lab. So next question is for Mike. Can you compare like the broad ion beam polishing with the PFIB?
Yeah, so I guess in both cases, I guess majority broad ion beam polishers is argon, I think. I don't have a ton of experience with it personally, but ultimately the idea there is that you do get the benefits of no gallium. You can do large areas, maybe even larger than the PFIB, but you don't have that endpoint detection ability. You don't have that ability to really stop exactly. You can't monitor while you're milling, so you can't really stop at that, let's say, buried feature that you're trying to hit. So in some cases, if you're looking at very, blanket films and things like that, that you're not really trying to do FA on, it could be very useful for you and maybe is the right way forward. But the versatility of the PFIB just really gives you all this other access to 3D reconstruction, endpointing, and things like that that you can't do with broad ion beam milling.
Okay, thank you, Mike. Sarah, there's a client asking, do you have any comments regarding using in situ etching to enhance contrast between different materials? It's more the same question. Okay. Oh, sorry.
Oh, sorry. So we do have different gas injection systems that can help mill or increase the contrast between different materials. So one commonly used gas is xenon difluoride, which will spontaneously etch pure silicon, but has a really low etch rate for silicon oxides and silicon nitride. So that's commonly used to decorate the surface of silicon. I think for other models, you can introduce like water vapor or like oxygen gas to increase the milling rate of some materials, like organic materials, but I haven't personally used that type of system before.
Okay, thanks. Adam, there's one more question about hydro. Are there advantages to using certain gases in PFIB over other gases? When using beam of nitrogen, oxygen, or other, can it react with other materials and form oxides, nitrides?
Yeah, great question. So yes, the different ion species allow for different use cases in different application spaces. Argon's really good at cross-sectioning for large volume cross-sections across similar materials, as mentioned earlier. Oxygen, has a chemical and a physical effect when milling, and so we use that to our benefit. A lot of the time, we do that on organic materials like packaging or life science samples, and it's a very, very surface level or surface layer of an oxide being formed. And again, it's very, very surface. And then nitrogen is still in the research phase. We have had customers use it for nitrogen doping and creating some nitrides, but that's still an unexplored space.
Great, thank you. I have one more question to you, Adam. So what is the maximum area that PFIB can do the delivery?
So it's based on the sample type itself. We see a wide variety. The most common is 40 to 100 microns, but we do see going up to 200 micron window sizes. But again, it's sample dependent. Yeah, and the transistor density level does play an effect on what size window is needed.
Okay, great, thank you. And client is asking, can PFIB do deposit? Yes, we can. And in our system, we have platinum, tungsten, and carbon. And Sarah, there's a question. What is the volume you can do the 3D tomography?
So that's a great question. It depends on a lot of things like your desired step size and basically the time you want to spend on the tool. So we can go up to like hundreds of, like maybe 300 by 300 by like 300 microns in volume, but that would take a really long data acquisition time. So I think it's usually wise to try and pick the smallest volume that will still get you the statistics that you need for your project based on the particle size or what you're trying to probe. But with PFIB, yeah, on the order of hundreds of microns, whereas for gallium FIB, probably just tens of microns.
Okay, great. So thank you, everyone. I think due to the time, this will be our last questions for today's webinar. Hi, Mike. How do we count for different milling weights on multi-material stack, ranging from polymers at ASIC, glass, PCB, etc.?
Yeah, I guess ultimately, I guess if you're talking about cross-sectioning, right, you end up seeing a lot of development of currents. We talked about the strategies to mitigate that. So by rocking mill, et cetera. In some cases, you can also try the different proprietary chemistries to try to help even out the milling rates. So that's part of the magic of the delayering process, as well as you essentially get a situation where the metals mill at the same rate as the insulators around them, so you can get this very planar removal. So that's one strategy as well. I mean, ultimately, it's sort of a cascading down effect in the cross-sectioning. So maybe controlling the geometry that you're attacking the cross-section at too can also help with that kind of thing. So you're not going along very, you don't have very dissimilar materials vertically, so you can go across that or something like that. So, experimenting a bit with the different things that you can actually control, right? And so we spend a lot of time doing that and developing our techniques here and how we can actually do certain things in reasonable amounts of time.
Thank you, Mike. And that's all about this specific topic. At the end, I'd like to talk about why we choose EAG. So there are several reasons, but I think it's important to state right at the top that client confidentiality is core to our business. We are a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering-related issues. At EAG, we have various certifications, accreditations, regulatory approvals, and licenses to support our clients' needs. Thank you.
And thanks again to Adam for joining us today. I really appreciate it. It really added a lot to it. And I know that I think that Thermo is having a webinar in the near future on Hydra specifically, and so please keep a lookout for that.
My pleasure. Thanks so much for inviting me. Really appreciate it.
Thank you, everyone. Just want to say again a big thanks to Dr. Adam Stokes for joining us today, and thank you to all of our experts for this robust discussion and presentation. And of course, thank you everyone for attending today's event. If we didn't get to your questions today, we'll be following up with you soon. If you have any other questions, please send in your questions to the email address on the screen. That is customerservice@eurofins.eag.com. And also want to mention that I've added a few links to our resources in the chat window, including a link to our next Ask the Expert event on wearable devices. So please check those out. Once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate your feedback. And on behalf of Eurofins EAG Laboratories and our experts, thank you for joining us today, and have a great rest of your day.
Thank you. Bye.